Hello all. Very good evening to all of you. I am Abhinav Chandrakar. I am a PhD student at Indian Institute of Science, working in Department of Materials Engineering. This is the doubt discussion session for the course Mechanical Behavior of Materials, which is being taken by Professor Sankran from IIT Madras, and it is being uh, conducted on NPTEL platform. This will be the fourth week of the doubt discussion session where we'll majorly focus on the contents of week 4. Let's wait for 2 more minutes, then we'll start. Hmm. Yeah. Let's start. Hmm. Firstly, we'll go through the a summary of the concepts which were taught in week 4. Then we'll move on to solving the old assignments of week 4. Also, there was a question on discussion forum about a query in a question of uh, week 4's assignment. So I'll also try to look at that. Hmm. Hmm. Yeah, I was just saving these notes before I edited. So, firstly, sir discussed about partial dislocations. Already, we have looked at dislocations in the previous week, where we saw that we can have two dislocations having two kinds of characters. One is edge dislocation and one is screw dislocation. In edge dislocations, the primary distinguishing characteristic is that the Burgers vector is perpendicular to the dislocation line, while in case of screw dislocation, the Burgers vector is along the dislocation line. So, in this week, we looked at partial dislocations, which are basically dislocations which were formed from a full dislocation due to the splitting of the full dislocation. And the reason they are called partial dislocations because the slip that is produced due to them is not a full atomic displacement, it's a partial atomic displacement. What I mean is that if that slip occurs, it will not lead to the atom going to a lattice position, it will go somewhere in between. So, in case of FCC, it is very readily observed, while in other crystal structures, as sir had mentioned, it is very rare to observe them because even though they will form, they will not be stable. Hmm. So for FCC, we know that the most favorable slip system is the 111 family and the 110 plane. Sorry, 111 family of planes and the 110 family of directions. And that is 110 is the Burgers vector. And when it splits, it can split into 2 bar 1 1 and 1 bar 2 1 bar. So it's split into two partial dislocations. And this will be favorable with when you use the Franck's rule to evaluate this. You can try that to see how the energy uh, changes due to splitting of the dislocation. So when it splits into partial, these two Burgers vector a by 6, 2 bar 1 1 1, these are not going to lead to a slip to a position which is a lattice position, while a by 2 1 bar 1 0 will take it to a lattice position. That's why they are called partials. And when partials form, for example here, there are two partial dislocations, and when they form a fault zone in between them, and locally the stacking changes. So if it was ABC AB, like as it is in FCC, locally it will become AB ABC and so on. So locally you have a HCP stacking coming in, and because there is a fault in the stacking, we called it a stacking fault. Mhm. There will be an energy associated with this also, which is called the stacking fault energy. Mhm. When it is at equilibrium, like the partial dislocations are at equilibrium, there will be a balance of forces. So there will be attraction due to the since there's some energy associated with formation of fault or some surface tension associated, the system will try to reduce that by bringing the partials together and constricting such that the partials will again form a full dislocation. So that will be the attractive force. But there will also be a repulsive force because the partials are having different Burgers vector. So due to the stress field between the two partials, there will be a repulsion between them. So that was about partial dislocations. One more point is that a dislocation will, so these are some of the salient aspects of dislocations. A dislocation will always move perpendicular to the dislocation line direction of the dislocation. and plane will always occur in the direction of the Burgers vector because that is the direction of slip. That is also one important point. And depending on what is the angle between the Burgers vector and the dislocation line, the nature of the or character of the dislocation will change from screw to edge, and in between we'll call it mixed, where it has both characters to some extent. Now, many a times when the dislocation is moving in your material, in the matrix of the material, it will experience some obstacles. It could be of different forms. It could be a boundary. It could be inclusion, precipitate dispersion, some small obstacle of that kind. Or it could be also other dislocations or falls, stacking falls, anything that changes the environment nearby and causes an impediment to the slip of the dislocations or glide of dislocation. That will be an obstacle. And in order to keep on gliding, since there's a shear stress being applied when loaded, so it will try to keep on gliding. It might many times have to bow around the obstacle, bow through the obstacles. For example, if it's pinned in two places, it will try to bow around. And the force which is required for the bowing to be successful. So once it bows around, it can form a kind of loop um, and then break away from the original dislocation, form a new dislocation, and keep moving. So sir has shown the steps of the bowing, the breaking off as a new dislocation, and the continued movement. So that you can see in his lecture. And but the shear stress associated with this is given by 2 GB by L. So L is the distance between the two obstacles. The smaller it is, the more will be the stress required to do the bowing of the obstacle and then do the bowing around the obstacle. Because a smaller dislocation, length of dislocation, you can see in the derivation. In the derivation, you'll understand. So just for now, I won't go to further explanation. I'll just say that the more the distance between the obstacles, the easier it is for this dislocation to go through. And this will have multiple direct applications in some of the concepts we'll see later, especially related to strengthening mechanism in the upcoming week. Then another uh, distinguishing aspect to screw and edge dislocations is that a screw dislocation due to its geometry, intrinsic geometry, can cross slip to other planes. So if its dislocation line is moving in a particular plane, it has the option to shift to a different plane and continue to glide on that new plane without changing its Burgers vector. So a dislocation Burgers vector can never be changed. It will remain the same for a particular dislocation. But screw dislocation can move to a different plane with the same Burgers vector, while a edge cannot do that. Sir has not in a lot of detail explained this. In short, he had explained. So the reason for this is that a screw dislocation has only a line associated with it because the Burgers vector is also along the same dislocation line. But a edge dislocation is defined by a plane because the Burgers vector is perpendicular to the dislocation line. That defines a plane. So it cannot change that plane. If it goes to a different plane, then the Burgers vector will no longer be in that plane. That's very likely. That's why a edge dislocation can only climb. And climb is a phenomena which involves the diffusion of vacancies, which leads to a movement of the extra half plane of the edge dislocation. So that was another difference between edge and screw dislocations. Now coming to interaction between dislocations, we had already seen what is the stress field due to one dislocation on another dislocation. We had seen that for screw dislocation, where we had told that for a screw dislocation, the stress field will only be shear, while for edge, it will be both shear and hydrostatic. Hmm. Yeah, it will be both shear and hydrostatic, and we had seen that like dislocations tend to repel, unlike attract, but in certain configurations, uh, depending on the mm, alignment of the dislocation, it can be either attractive or repulsive. We had seen that for edge dislocation, so that how the angle theta between two dislocations can lead to change in the attraction or repulsion between the dislocations. Coming to interaction between parallel dislocations, Hmm. the if you have two dislocations, and by parallel we mean they are along the same line, then in that case, the force between the dislocations can be given by C B1 B2 by small r. So this is as a function of distance between the dislocations, and in case of change in the angle theta between dislocations, it will be given by this expression for edge, and it will be zero for screw. So because um, a screw dislocations stress field is much more simpler and it is more symmetric, it has circular symmetry, so it will not depend on theta, it will remain the same. But for screw, but for edge, it will depend on what is the angle between the dislocation line. So we can see that this has these two dislocations being kind of on the same slip plane, but at different angles with respect to each other. Yeah. So it can be even negative. So let us just see. Yeah. If theta is more than 45 degree here, then sine theta, sorry, if theta is more than 90 degree, then sine theta will be negative. While if it is less than 90 degree, then sine theta will be positive. So the force can be either attractive or repulsive. And as we had seen earlier, the constant will be different for screw and edge. For edge, the force will be higher, just the same way in which the energy is higher for edge dislocation than screw dislocation. So in a similar manner, the force exerted by edge dislocation is also higher. That is, the stress field itself is more. So earlier we had in the previous week we had briefly discussed that dislocations will tend to arrange themselves in certain configurations which will be associated um, with lower overall energy. Those configurations which are somewhat stable, or you can say metastable, they have lower energy, and usually these are configurations where the tensile and compressive stress field tend to cancel out each other, thus leading to lowering of energy. One such very common case is the formation of till boundaries, where primarily edge dislocations tend to align over one another, and because of this, there is some cancellation of the stress field, tensile and compressive like portions of the stress fields of the dislocation, and it has a lower energy. This is also associated with an angle of misorientation, which is developed due to the till boundary, due to existence of till boundary. It has been discussed in the lecture. Now we had already looked at bowing of dislocation, stress required for dislocation to bow. So we will now take that forward through one phenomena which involves the bowing of dislocations, and that is multiplication of dislocations by a Frank Reed source. Usually this source is some obstacle, and when dislocation goes through, what the outcome at the end is that it will form a new dislocation loop, which will which can keep moving forward, like without any impediment. And so because of the phenomena, again it's the visualization of this is shown in the lecture. But what happens is that due to the Frank Reed source, the dislocation bows, it forms a new loop and cuts off from the original dislocation, and it can keep gliding freely. So in this way, new dislocation loops keep on forming, and that's why this is called a source, a Frank Reed source for multiplication of dislocation. And the stress required for the activation of source is again the stress required for Boeing 2 GB by D. And D is called the size of the source. It could be some obstacle. It could be due to dislocation being stuck at the boundary of two slip planes. And it could also be due to some grain boundaries. Grain boundaries are of Frank Reed source. So all of that. Or dislocation is just tangled together, which are also a form of obstacle. Hmm. But one another aspect of related to Frank Reed source is that over time, uh, as the dislocations pile up, as the dislocation loops form, they will act as a they will repel the incoming dislocations which are coming towards the obstacle or the source. So the more dislocation loops form, the more they will repel the incoming dislocations, and as a result, they will make it difficult for the source to continue operating, since they have this repulsive force, which can also be called a backstress. Um, the source will find it more and more difficult to operate. More stress will be required for the incoming dislocations to reach the obstacle. Yeah. Now, hmm, coming back to partials. So we have already talked about partials forming in FCC, and this happens so that the overall energy of the dislocation can reduce. But since we have already seen that screw dislocations tend to cross slip, when a partial, when it has split into partial, because the partials do not have a completely screw character, they will have some edge character also. They will not be able to cross slip directly to another plane. So cross slip is a mechanism by which screw dislocations can overcome obstacles if there's an obstacle in their gliding path. Just give me a minute, I'll continue on this topic. Sorry. Hello. Yeah, let's continue. Yeah, so we were talking about partials. So partials also, screw dislocation can cross slip, but partials have some edge character also. So that will restrict the cross slip phenomena. So in order for a screw dislocation to cross slip, the partials which were formed due to dissociation of the screw dislocations will have to come together. Then it can cross slip, and then they can again dissociate to reduce the energy associated with the dislocation. So this phenomena of recombination of partial is this phenomena of combination is called recombination. And this recombination will require some stress because there is a repulsive force associated the with the two partials, which keeps them separated from each other. So in order to bring them together, you have to supply some energy through stress firstly, and also through thermal energy, the intrinsic thermal energy associated with the material for that temperature. Yeah. So this tendency for recombination will depend on what is the stacking fault energy for that material, because as I said, the partials are separated by a stacking fault, and if the energy of that stacking fault is very low, the partials will be far away from each other and it will be difficult for them to recombine. While if it is very high, the partials will be very close to each other to reduce the stacking fault area. And since they are close, it's easier to recombine. So cross slip will be easier. So by using this uh, thought process, we can say that low SFP materials will have difficulty in cross slip due to more spacing between the partials, and as a result we expect that they will have more of planar slip and less of slip into different planes. Hmm. Now we'll also look at how uh, since you can have a very high density of dislocations in material in usual recrystallized material, which is like has very low deformation, it has been annealed at high temperatures. So even in those kinds of materials, and also it has recrystallized grain, we expect low dislocation density, but still it has a value of up to 10 raised to 12 per meter square. 10 raised to 12 per meter square, that is the unit of dislocation density. And when you cold work it, it can go up to 10 raised to 16 also, 15 or 16. So about increase by an order of 4 after a cold working and heavy deformation. So the reason I brought this up is because I want to convey that metals in general will have high dislocation densities, like a lot of dislocation. So these will also interact with each other. They will have stress fields which will interact with each other. And as a result, this will affect the phenomena which occur inside it. So because of so many dislocations, many of them will be intersecting and they will be an obstacle to any other dislocation which is gliding through the material. And so in this way, they can reduce the mobility of the dislocations which are gliding in the specimen. And this can lead to phenomena which we call work hardening. Basically, it becomes difficult to strain the material. The material becomes harder, and that is because the dislocations mm, are facing the dislocation mobility is reducing due to this kind of dislocation tangles or dislocation forests which are forming. So another phenomena which takes place due to intersection of dislocations is the formation of jogs. So sir has explained in good detail, and he has explained quite well how jogs form and what can be the effects of it. So if you are forming a jog due to two screw dislocations or a screw and a edge dislocation, the resulting jog tends to be mobile. So one thing to keep in mind is that when these jogs are forming due to intersection, the jog portion of the dislocation will have a Burgers vector which will remain the same as that of the previous dislocation. The line direction will change depending on the Burgers vector of the incoming dislocation, but the Burgers vector of the jog will remain the same as the one of the original dislocation. Yeah. Is there any doubt? Hi, Monik. You want to ask anything? You can mute yourself if you do not have any question. Mhm. Okay, I'll continue. If you have any question, you can let me know. So we talked about jogs, how to understand what will be the Burgers vector and line direction of the jog, because that will decide what is the character of the jog. So a jog for a screw dislocation can be an edge, can have edge character and vice versa. So the important thing to understand here is that if you have two screw dislocations getting cut, then the jog will be edge dislocation and it will not be on a slip plane. So in that case, it will be immobile. In other cases, it will be mobile. So two screw dislocations cutting each other will lead to immobile jog, and that will drastically reduce the mobility of the entire dislocation since the portion of it cannot move. So it's like kind of trapping a dislocation by fixing one portion of it. And the movement of this portion can lead to production of vacancies and interstitials. Also, sir had mentioned that interstitial producing jogs are more likely than vacancy producing jogs. The edge the edge components can always move by climb, which I said was a dislocation, no, sorry, diffusion based process. So since it involves diffusion of vacancy, to be having a appreciable contribution to dislocation motion, it requires high temperature since the thermal energy uh, at high temperatures is higher. So this can be used for making the atoms jump to next position, and this is what diffusion is about, right? Atoms moving from one position to another due to the thermal energies. So climb is uh, only so relevant at high temperatures. Now coming to the quantification of the strain due to dislocation motion and relating dislocation densities to macroscopic strain, so that we can relate the response of a material to the state of the material, that is the dislocation density or structure of the material. So sir had shown through sir had derived that if you have a dislocation density in your alloy of rho, that is length of dislocation per unit volume, and B is a Bajaj vector, and the dislocations move on an average by a distance x bar. Then the strain due to it will be equal to rho b into x bar, and the strain rate will be rho b into v bar, the mean velocity of the moving dislocations. Now, dislocation will have a associated Bajaj vector. Sorry, of course, the Bajaj vector and dislocation line. But when we try to understand the stress required to move a dislocation, then we'll have to look at what are the stress fields associated with the dislocation, because that will affect the activation required for the dislocation to move. That is the atoms to switch their bonding. So if a dislocation has a stress field which is very concentrated near it, that will make it difficult for the atomic bond switching to take place. But if the stress field around it is diffused, then it will be easier. So width of a dislocation, or a characteristic width, is basically an indication of how much is the distortion, to what length scale is the distortion which has occurred in the alloy. So if the width is high, that means the distortion is over a larger area, and that in a way signifies that the distortion is not concentrated, so it will be easier for the dislocation to move. But if the distortion is concentrated, that is the width is very low, then the movement will require a very high activation energy, because um, the process involving bond switching, it will be difficult for that scenario. Sir has shown it visually very well in his lecture. As a result, the PN stress, which is the stress required, pulse Nabarro stress, which is the stress required for dislocation to move, will depend on the width of the dislocation, and which in turn depends on the bonding forces. So if the bonding is such that there's a spherical stress distribution, then the dislocation width tends to be large, while if it is directional, then it tends to be small. The width tends to be small, and PN stress is higher. Uh, it's For alloys, it tends to be spherical. For example, for CCP structures, cubic closed pack structures like FCC and HCP. While for directional ones, such as ionic bonds or covalent bonds, the uh, width is lower, and correspondingly, it's very difficult for a dislocation to move. And that's why the plasticity also is low in such materials. Now, PN stress depends on the short range stress field of the dislocation core. So same thing which I told earlier. At a very localized region, what is the stress field or distortion that has occurred in its environment? And so this will be sensitive to the temperature. If the temperature is higher, then the intrinsic thermal energy or vibrational energy of the atom is more. So that can be utilized in the as an active in that can be utilized to fulfill the activation energy required for atomic jump to occur, and the dislocation to move. So PN stress will be lower if the temperature is higher. It is also called yeah. Another fact or another point is that wide dislocations will have a lower temperature dependency of the PN stress compared to uh, smaller with dislocations. So as a result, these FCC alloys tend to have a lower dependency of temperature, PN stress on temperatures. So that was all which was covered in week 4 lecture. So I think I have delved in good amount of detail. I have explored it in good detail. I suggest that you go through the lectures to look at the visualization and images that Shar has used to teach it. Now we'll move on to the assignment questions. Uh, week 4 assignment. Hmm. Let's take a 5-minute break and then we'll resume with the session. Till then, you can try to solve, start solving some of these questions if you want. We'll take a 5 to 10 minute break. Hello all. Let's resume with our assignment solving. This is the assignment for week 4 of previous year. In the first question, we have been told that a dislocation segment is spin by two dislocations, two obstacles at a distance of 10 microns. What will be the stress required to bow the dislocation around the obstacles? So we know that force will be equal to 2 GB by L, and this is going into a semicircle, right? So this is the highest stress that will be required for the Boeing to take place. So F equal to 2 GB by L equal to 2 into 40 GPa into B is, pardon my handwriting, 40 GPa into 0.25 nanometers divided by 10 micrometer. So this will be equal to 8 into 0.25 GPM is 10 raised to 9, nano is 10 raised to minus 9. So it will end up as 10 raised to minus 6, right? 10 raised to 6. So this will be equal to 2 megapascal. So the correct answer is 2 megapascal. Let's go to the next question. Which of the following statements is or are correct? Oh. Firstly, I will Mhm. Mm, mhm. I've removed all the answers. Now let's continue. Which of the following statements is or are correct? Crankcrete mechanism is a way of generating new dislocations. That's true. Highest shear stress is required to overcome the crankcrete source of dislocation. That is also true, and we have seen what is the value of that shear stress. A dislocation can only move on a plane containing the dislocation line and the direction of Berger's vector. That is also true because The Burgers vector, which is the direction of slip, or the direction in which the atomic bonding switching is happening, has to be on the same plane on which the dislocation is moving. Sorry, this is not a good way of putting it. So the Burgers vector of a dislocation cannot change. So the Burgers vector, which is the direction, has to lie on the plane on which the dislocation is uh, mm, the dislocation can only move on the plane which has the Burgers vector on it. If a plane does not have that direction lying on it, then the dislocation cannot move on that plane. That is the right way of putting. And of course, it's a dislocation line, so the line should also be lying on that plane. So overall, we can say that a dislocation will have a slip plane associated with it. The only exception is a screw dislocation, because there you only have a line. You do not have any Burgers any separate yeah, plane associated with that dislocation. Multiple planes can be associated. So C is correct. I hope my explanation was fine. D, in metals with low stacking fault energy, dislocation cross slip is easier to occur. So we have seen that the stacking fault energy, if it is low, that means the spacing between the partials will be higher, because the attractive force, that is the energy due to the fault, will be lower. Since the partials are away from each other, it will be difficult to recombine them, and therefore cross slip will be difficult, because cross slip requires recombination. So this will be false. The correct answer is A, B, and C. Yeah. Question number 3. Assertion is edge dislocation cannot cross slip on different planes. Reason is the Burgers vector for an edge dislocation lies perpendicular to the dislocation line. Yeah, we know edge dislocation cannot cross slip. The reason is also right, because the Burgers vector is perpendicular to the dislocation line. This defines a plane for that dislocation, and the dislocation will have to be restricted to that plane only. It cannot move on a different plane. As I said, dislocation can only move, sorry, the Burgers vector will always have to lie on the plane on which dislocation is moving, because the slip is occurring on along the Burgers vector. So the slip can only occur on the slip plane on which the dislocation is moving. Otherwise, the dislocation won't move if the plane, it will not move on a plane which does not have the Burgers vector lying on it. Therefore, in this kind of a case where you have a edge dislocation, the edge dislocation will not be able to cross slip to a different plane. It has this restriction. So both the assertion and reason are true. And the reason is the correct explanation of the assertion. Next question is, you have a moving edge dislocation which is pinned. A shear stress is applied to drive another dislocation towards the first dislocation. Then what will be the equilibrium separation between the two dislocations? Okay, this is a good question. And it's a edge dislocation. Yeah, we have a edge dislocation. Uh, Another identical dislocation is moving with the same Borges vector on the same plane was the first one. Hmm. What will be the equilibrium uh, facing? So we know that the dislocations will repel each other because of the repulsive nature between two dislocations which are lying on the same the line connecting the dislocation. Hmm. Let me rephrase. Okay, since the two dislocations are mm, exactly parallel to each other, they will repel each other, and we also know the expression for the repulsive force. It will depend on the distance small r between the dislocations. I think we had seen it was something like gc into a constant into b1 dot b2 by small r, where your constant is g by 2 pi into 1 minus mu in case of edge dislocation, right? Let's just confirm if this is what it is. Mhm. Yeah, it's this only. Force per unit length of the dislocation will be cb1 b2 by small r. Okay, so okay, let me just write this better. So if you have dislocations on the same slip plane, the line joining them, it is at an angle of 0 degree, right? Because the this line joining them is parallel to the slip plane. But if you have dislocations on two different slip planes, maybe here and here, then in that case, the line joining the two dislocations on these two slip planes will be at an angle theta with respect to the first one. So in this case, your expression will become C B1 B2 by small r into sine of 2 theta, right? Yeah. But here we have theta equal to 0 because they are on the same slip plane. So we can use this expression g by 2 pi into 1 minus mu into b1 b2 by a small r, which will be, so force will be equal to, we have g equal to 2.1 GPa divided by 2 pi into 1 minus 0.3 into b1 b2. For FCC, what is the Burgess vector? It is equal to a by 2 110, and a by 2 110 has a magnitude of a divided by root 2. So 0.353 nanometer divided by root 2 whole square, since both the dislocations have the same Burgers vector into 1 by r. And the spacing between the dislocations is r in nanometers. So let me write the r dot n. N refers to nanometer. And this, if it is equal to 150 megapascal, then the forces, repulsion and the attraction force or the driving force is 150 megapascal, which is bringing both the dislocations together. So when F is equal to 150 megapascal, it will lead to force balance. So it will be at equilibrium. So what we need to do is we need to equate the value of these two expressions and find out what will be the equilibrium space in small r. So r dot n equal to 210 GPa by 2 pi into 1 into 0.7 into 0.353 square. So n to n square. N means just the nanometer 10 raised to minus 9, that scaling thing for the unit, divided by 2. So this n can cancel out. Then we can simplify this as, let's just calculate it. Okay. This is coming out as 2 into 2.97 uh, G into n is 10 raised to minus 9, like with respect to SI unit. So 10 raised to minus 9 meter. GPA is 10 raised to 9 pascals. So this becomes overall, it is equal to 2.97 nanometers, because R was in nanometers, the way we had done it. 2.97 nanometer. The correct answer, is point up to 0.255, but we are getting 0.29. Let me recheck the calculation. So if I'm putting the exact value of A, I am getting it as equal to 2.6. Let me do it again. Just give me a minute. Yeah, I'm getting the same answer. Hmm. I'm not sure if this uh, answer key is right or not because we are getting this as the value. Ah, anyways, let's proceed. So this is the answer it is I'm getting, which is slightly different from what they have put. There's no, this is not slightly different. They have put it 0.25 nanometer. We are getting 2.9 nanometer. So it's a big difference. Okay, so here I also have to put 150 by 150 megapascals. We did not take that into consideration. So let's do this again. Now it comes out as 0.198 into Gn by m. Hmm. Things are not matching up here. So this is the force per unit length under dislocation. Okay. So this will not be equal to 150 megapascal because 150 megapascal is not a unit of force, it's a unit of stress. So let's just clear this and start again. So we have to equate the it to 150 megapascal of shear stress, but the force will be equal to tau b, right? F is equal to tau b on a dislocation, tau dot b. And since the shear stress is can be, it can be assumed that it is along the Burgess vector. So then force will be 0.353 n by root 2 is the force, which will uh, which will have to be equal to the repulsive force for equilibrium. So now equating both of these, Rn should be equal to 210 G by 2 pi into 0.7. So one Burgess vector will get cancelled out. So you'll only have 0.353 n by root 2, then 1 by R into n, 1 by 150 m. This will be equal to, now let's see what comes out. So that's a good question. You have to uh, combine two concepts. One is force on a dislocation due to a shear stress, and other is the repulsive force between two dislocations at a particular distance from each other. So let's not put it as nanometer here. That won't be right. So this is the force in SI units. Sorry, and here it is the spacing in SI units. This is coming out as 0.079 into 10 raised to minus 6 meters. This is a very high value. Hmm. Okay, I'll have to look more into it. I'm not sure where I'm going wrong. This is about 79 nanometer. While the answer is something else, I know. Yeah. So I'll have to check this one. I'll again, I'll try to look up with the solution maybe and let you know in the next session what is the correction. So let's just move to the next question now. We have many questions still remaining. The interaction of two dislocation lines E and F under the influence of applied stress is shown in the lecture 7 at 15 minutes. The Burgess vector of E and F are B1 and B2 respectively. What is the magnitude of the jog formed in E? Mhm. The jog formed in E is due to the dislocation F, and F has a Burgess vector of B2. So that will lead to a formation of a jog of length B2 in E. So the length of the dislocation, the jog in dislocation E will be B2. What is the magnitude of jog formed in F? So in similar way, uh, the length of jog formed in F will be equal to Burgess vector of the dislocation which caused the formation of the jog, which is E. So B1. Question number 7. FCC single crystal is sheared by gamma 12 equal to zero point 0.3. If the dislocation density remains constant, the average distance each dislocation will have to move will be. So dislocation density is constant and it is mentioned. Burgers vector is known. Then we have been told that gamma is equal to 0.3 and mu is equal to 0.3. Mu 12 means the shear component, the 1 to shear component of the stress tensor. So first row, second column, or uh, along the shear on plane 1 along direction 2. So for this we can say that we know that question number 7. So here we already know that shear strain due to dislocation, movement of dislocation is equal to rho b x bar, the net, average distance by which the dislocations have moved. And there's one more term missing by, I think, the total height of that material, I guess. Yeah, it's rho b x bar, and yeah, it's just rho b x bar, where rho is equal to number of dislocations per unit volume. So, sorry, number of dislocations per unit area by L into H. Um, yeah, the length, total length over which the dislocations have to travel to cross from one surface to another, and H is the height of the material. So here we know that uh, the shear strain gamma is equal to 0.3. Rho is equal to 10 raised to 7 centimeter raised to minus 2 into Berger's vector is 0.31 nanometer into So one peculiar thing about the previous question's answer key is that the answer was 0.24 nanometer, which will be less than the, yeah, so that answer will be less than the atomic spacing, which is 0.35 nanometer. That also suggests that the answer might be wrong. The dislocations cannot be closer than the atomic spacing, lattice parameter. Hmm. I'll try to see later. We got it as 0.79 nanometer. So here you have rho into b into x, the mean distance that dislocation has traveled. So x will be equal to 0.3 by 0.31 into 10 raised to minus 7 by 10 raised divided by centimeter raised to minus 2 into 1 by nanometer. So this will be equal to approximately equal to, let's say, 1 into uh, let's do the unit conversion. 10 raised to minus 7 into centimeter square. 1 by centimeter square to meters will be 10 raised to minus 4 here, divided by nanometer is 10 raised to minus 9, and this will be meters. So this is approximately 10 raised to minus 2 meters, 1 centimeter, about 1 centimeter. The exact answer will be slightly less than that. Hmm. Exact answer is 0.967. Yeah, so it's fine. Now let's go to the next question. Here we have a step formed in the parent dislocation. Which of the following is true about it? First question is segment CD is a kink. Mhm. So we have a dislocation AB, and there's which is on a so AC is on one slip plane, DB is on a parallel slip plane, and CD is on a different slip plane. Assuming that the Burgers vector is the on the plane having AC and DB, um, a portion of it is not on the same plane. Hmm. So can we call segment CD a kink? A kink has not been taught as far as I know. I did not notice in the lecture. Let me just check what is the formal definition of a kink. A kink is a step in the dislocation line that lies within the glide plane. Okay, this was, I think, just mentioned by sir. So if a portion of dislocation lies outside the glide plane, it is called a jog. So if the step is outside the glide plane, it is jog. If it is inside the glide plane, that is lying on the glide plane, it is a kink. And they can move along the dislocation line. Move along, okay. So since it is likely that uh, so actually if CD is also if this is a screw dislocation, um, yeah, this cannot be a screw dislocation because CD is having a different direction compared to BD. So Burgers vector of BD will then not be the same as that of CD if this is a screw dislocation, because screw dislocation has Burgers vector along the dislocation line. Mhm. So a part of the dislocation is lying on a different plane compared to the other path. So if AC or DB is the glide plane, CD is not the glide plane. So likely CD is should be called a jog because it will not be falling on the glide plane. So answer should be false. Next question is if dislocation line ABCD has to move under the influence of tau A only, the motion of the segment CD is non-conservative. Mm, so non-conservative motion refers to a motion which requires movement outside the glide plane, usually by addition or removal of vacancies or interstitials. So it could be a climb kind of process. So if the shear stress tau is applied, then the motion of the segment ZD will be non-conservative. That is what is asked. I think yes, if CD does not fall on the glide plane, which we have already confirmed, it depends actually on what plane CD is. Uh, if it's a slip plane, mm, sorry, if it is a favorable slip plane that is having low CRSS or PN stress, then D could also be on the glide plane. So it's difficult to say, but I think it should be true that it will be non-conservative. But here it's written false. So we'll have to look into it. It's difficult to say if we do not know the which is the glide plane, then it is difficult to say. Or what are the slip systems, whether all of them are or what is the Burgers vector, that also we do not know. It's difficult to say. If the dislocation line ABCD has to move under the influence of TB only, the motion of segment CD is only possible at higher temperatures. Okay, so tau B is applied. So dislocation has to the Burgers vector. So here the strain occurred along tau A, but now it will occur along tau B. Okay, I get it now. So one way to try to rationalize this answer is that if you have tau A only, then the slip will occur along tau A. So Burgers vector, the component of Burgers vector along tau A will be deciding the direction of slip, right? So here the component of Burgers vector along tau A will be lying on this slip plane, right? So it is in the slip plane, so it can glide. It we can consider it is a as a glide plane. So the motion will be conservative. That way we can rationalize it, and using the same logic, if the strain is along B, so tau B, so the component of Burgers vector along tau B will be important, and that will fall. Uh, that will not fall on the glide plane. It will be parallel to DB, right? Which is not on the glide plane. So for the portion CD, the movement will be non-conservative since the component of Burgers vector which is along tau B is not on the slip plane having CD, while it is for tau A it was on that slip plane. So the correct answer is true. I guess that can make sense. Yeah. Mhm. Okay. So with that, we'll finish this assignment. There was a question in discussion forum about assignment 4, question number 10. Let me quickly look at that question. So in that question, we you have two parallel and straight screw dislocations. In copper, the dislocations are separated by distance of 0.12 nanometer. They are of opposite sign. The total force on each dislocation is to be calculated. For this, you will require the value of G, the value of D, grain size is given, which is okay, and the distance has been given. So if distance is given and the signs are given, you have to tell what will be the value of the force, and also whether it will be positive or negative, you have to include in that. So I think that you can use the value of shear moduli and the Burgess vector for pure copper. Also, copper is FCC, so you can get Burgess vector from the known literature and use that. So that should be fine. So with that, let me finish this session. Thank you all for attending. Goodbye.
Thank you, sir. Sir, one doubt is
Yeah,
there.
yeah.
Can I
Yes,
ask? So
sure.
today you have solved week 4 problems, right, sir?
Yeah, yes.
So in my login, in my account, those questions are not displaying. It is a different questions I have.
Yeah. So actually, these are not from the current year's assignment. They are previous year's
Okay.
assignment. I have uploaded it in the questions in the shared folder. Because the assignments have to be first submitted by you all, then only I can discuss for the current year.
Yeah, sir.
So
Last
first
date
you
is
need to
tomorrow.
attempt by yourself. So
Yeah.
attempt it by
Mhm.
yourself. It's
Yeah.
very similar
Already
to the ones
attempted.
I solved in this session.
In
So
the
just
next session, you will attend those problems, sir.
in the if there are any doubts, you can let me know. Then I'll attend it.
Okay.
Or you can post in the discussion forum.
Okay, sir. Okay. Thank
Anything
you.
is fine. Thank you for
Thank you.
attending. Yeah.